Hello, my name is Giorgio Mariani and I am here to present the work done by me and my colleagues for the Symposium on Geometry Processing 2020. This work consists in the generation of adversarial examples using perturbations that are limited in the truncated spectrum of the Laplace-Beltrami operator. For this work I have been assisted by Luca Cosmo from Sapienza University and the University of Lugano, Alex Bronstein from the Israeli Institute of Technology, and Emanuele Rodolà, again from Sapienza University. What are these adversarial examples? Using the words of Goodfellow, these are slightly perturbed inputs that result in the model outputting an incorrect answer. An example is this image of a panda, which is correctly classified by the model. However, by simply adding this adversarial noise, it is possible to produce an imperceptibly close image, this one, which is however misclassified as a gibbon, with high confidence. These type of adversarial attacks are common in several types of deep neural networks architectures, and may hinder their applications in the real world. Speaking of real world, here we can see another interesting work that associates adversarial examples with real-life applications. The authors were able to produce adversarial examples by directly applying black and white stickers, that we can see here, to a stop sign. Of course, this work shows the danger of deep architectures if used for safety-critical tasks, such as autonomous driving. Adversarial examples have been found in several types of architectures and several types of data, such as images, sound recordings, and even graph data. For example, we may be able to change the output of a graph classifier that predicts the political preference of a group of people by simply adding a couple of vertices or edges, as we can see in the image. Surfaces and point clouds are also among the domains in which adversarial examples have been studied. Here we can see two early works that apply variation of existing adversarial attack methods in the world of three-dimensional point clouds. Particularly interesting is the work done by Xiang and others here, in which both shifting and addition of points are possible attacks. This is of course quite different from the image domain, where shifting is the only possible option. Furthermore, the surface domain is fundamentally different from the image domain, and while we are used to see discontinuities in pictures all the time, think for example of edges and occlusion, we are less used to see discontinuities in surfaces. Hence, a more effective attack would probably try to preserve the geometry of the surface. Here we can see a couple of attacks that do not enforce surface preservation, resulting in quite noticeable adversarial examples. This is especially true for meshes, while it may be less visible for point clouds. We are not the first authors that notice this problem, and some work has recently been done to prevent this type of high-frequency noise. This is usually performed by applying a regularization term that forces perturbations to be smooth. For example, the approach on the left, which I believe was published in April this year, uses regularizers that causes points to move towards the centroid of their neighborhood, up to a certain threshold. While this indeed makes the perturbation smoother, it may also cause loss of information of the original shape. The method on the right, however, causes the curvature of the original surface and the curvature of the adversarial surface to be similar. This type of attack seems to yield better results than the previous one. However, it can still suffer from high-frequency noise when dealing with challenging adversarial attacks. Differently from previous work, our approach tackles the problem of preserving the original surface in a different way. Instead of a regularization term, we want to constrain the perturbation to avoid sharp discontinuities, hence preserving the shape. The way we do this is by representing the perturbations in the truncating eigenbasis of the Laplace-Beltrami operator. I want to emphasize that we search for smooth perturbations, but do not intend to smooth the actual surface. If the surface has discontinuous behavior, we would like to preserve that. We also tested different similarity measures than the one usually applied for adversarial examples, which typically are the L0, L2 or L-infinity norms. The Laplace-Beltrami operator is a differential operator common in the world of geometry processing. It is defined as the divergence of the gradient, and it possesses a number of useful properties, one of which is that any square integrable scalar function defined on the surface can be represented as a linear combination of the operator's eigenfunctions. Another useful property is that by truncating this linear combination to the first k elements, it is possible to obtain a smooth approximation of the original function f. On the left, the original function is plotted on the mesh, while on the right, the approximated truncated function is shown. In particular, here we can see the behavior of this approximation while the parameter k is varying. A smoother approximation is achieved with smaller k's, while a finer one can be obtained with higher k values. In our setting, we exploited this truncation property by considering a perturbation as three scalar functions, one for each coordinate dimension, and then by applying the truncation of the eigenbasis in order to achieve the desired smooth perturbation. Here on the left, we can see a random perturbation on all the vertex positions. This perturbation is very noisy and doesn't preserve the local surface. On the other hand, the truncated perturbation, even if less expressive, tend to better preserve the original surface, which is especially true when working with less eigenfunctions. It is interesting to see how, with higher number of eigenfunctions, finer noise starts to be seen also in the truncated perturbation. In our work, we applied this perturbation truncation to two existing methods, one for targeted attacks, in which we prescribe the output class for the perturbed input, and one for the untargeted scenario, in which we are simply interested in causing misclassification. For the targeted scenario, we use a variant of the well-known method by Carlini and Wagner. Here we can see its original formulation, which minimizes, using gradient descent, this ensemble loss, which is composed by two terms, one that controls the distortion of the perturbation, denoted by D, and one controlling the effectiveness of the adversarial attack, which we name H. The distortion in standard Carlini and Wagner is simply obtained by the norm of the Euclidean distance between the original input and the adversarial example. On the other hand, the adversarial loss H is used to ensure that the adversarial perturbation is actually able to misclassify towards the target class. Intuitively, it does so by reducing the distance in the output distribution between the model prediction, which is the argmax among the logics, and the target class. Finally, the parameter alpha is estimated using binary search, searching for the smallest value such that h is 0. We can see here the results of applying Carlini and Wagner's method over a surface without adopting any surface preservation precaution. Similarly to the previous random perturbation, the local geometry is lost in several other areas of the surface, and particularly faces and ends and feet. Generally speaking, all the finer details are removed by this approach. Instead of optimizing for a simple additive perturbation, we propose to optimize over the spectral coefficients of the truncating eigenbasis. We can see that now the adversarial example is preserving the surface in a more natural way due to the limited nature of the perturbation. We also discovered that we would usually achieve more natural looking adversarial examples by substituting the distortion term with a function promoting the preservation of the metric between the original surface and the adversarial examples. We do this by penalizing the distortion of local Euclidean distances. In contrast to classical L2 norm penalty, used in previous work, this formulation allows larger displacement of the surface points as long as a certain degree of local rigidity is preserved. As we can see in the animation in the right, this perturbation seems to be particularly suitable for deformable surfaces. We also applied our band-limited perturbation to the fast gradient sign method, which is designed for fast untargeted attacks. It uses the gradient of the cross-entropy loss L in order to identify the direction in which it is locally maximized, thus moving the adversarial example towards the direction that produces the most locally different output distribution. The movement is constrained by the parameter epsilon, used for clipping the displacement from the original vertex positions. The process is iterative, and the step size is modeled by the parameter alpha. In our variant, we divide the recursive formulation into two variables and apply a low-band filtering operation during computation. The subdivision into two variables is necessary in order to avoid the smoothing not only of the perturbation but also of the underlying geometry, which of course would be very noticeable when working with a small number of eigenfunctions. The main difference with standard fast gradient sign method is that we do not iteratively update the adversarial examples, but we update the adversarial perturbation instead, and in order to get the actual adversarial example, we simply sum the input coordinate x to the perturbation. There is, of course, a non-trivial trade-off between the smoothness of the perturbation and its expressivity. More eigenfunctions mean a more powerful perturbation, which, however, may contain higher frequency noise, while fewer eigenfunctions means smoother and simpler perturbations, which, however, may be less effective. How to choose this value may very much depend on the classifier model and on the surface we are trying to perturb. For our experiment, which consists mainly of human faces and animals, the optimal value seems to be around 40 eigenfunctions. During our work, we used different datasets of deformable shapes in order to experiment with our adversarial attacks. In particular, we used 3 existing datasets and we generated a further one using a parametric model. The datasets we used are the Faust, Shrek and Coma datasets. Faust and Shrek's 14 contain meshes of people in several poses, hence they can be used for pose categorization tasks. Also, due to the lack of correspondence between shapes in Shrek 14, we decided to use its surfaces as point clouds, while Faust, Coma and Small were used for experiments with meshes, since correspondence is available. The Coma dataset contains several shapes of face in different extreme expressions. We used this dataset in order to train a classifier to identify people. Small is a parametric model for animal shapes. In particular, 5 categories can be represented: cats, dogs, horses, cows and hippos. In order to create the dataset, we generated a number of meshes using the parameters available at the model's website. While using this dataset, we trained our classifier in the recognition of the animal species. Here we show a comparison between our attack and the standard Carlinian-Wagner approach. We are able to produce perturbations that are both less perceptible and more meaningful, since they are more aware of the surface geometry. In particular, we do not introduce any high-frequency noise due to how we generate our perturbations. We can see here some other qualitative results of our adversarial examples. The top surfaces, here, here and here, are the original shapes, while the one at the bottom, here, here and here, are the actual adversarial surfaces. An interesting property of our adversarial attacks is that they seem to be able to find semantically meaningful regions of the surface to deform. This is probably due to a combination of the localization properties of the Laplace-Beltrami eigenfunctions and our metric preserving term. Using our fast gradient sign method variant, we were also able to augment the original datasets with adversarial examples. This type of dataset augmentation is referred to as adversarial training. The advantages are usually twofold. The model learns to be more resistant to adversarial examples, and its accuracy can be increased thanks to the new inputs during training. In conclusion, in our work, we designed a novel method for the generation of adversarial surfaces, which works particularly well for deformable shapes, by utilizing properties of the Laplace-Beltrami eigenspaces. Thank you all for your attention, and I hope you have a nice day.